going to say attributes. Okay? So, esta es una gran oportunidad. Yo voy a mantener esto lo más corto posible. Lo importante no es lo que yo voy a decir, sino que él va a decir. Pero sí hay que decir, profesor Martínez, más de 160 artículos, es autor o coautor de 20 y tantos capítulos de un libro, editor de otros 20 y tantos. Su trabajo ha sido citado más de 10.000 ocasiones. Dirige un grupo enorme, uno de mis estudiantes de doctorado, Marta, que ustedes la conocen, está con él allá. Es realmente una oportunidad diferente a la que somos nosotros. Es para que oigan al exterior. Como decía, es una gran oportunidad de ver una química diferente a la química que hacemos nosotros, ¿bien? Que puede abrir puertas para colaboraciones. Las ideas de estos intercambios no es venir a alardear de lo que hacemos. Cuando nosotros vamos a otro sitio, vamos a alardear a lo que hacemos. Vamos a exponer lo que nosotros hacemos y eso es la fuente de intercambio, de buenas relaciones. Yo me alegro de que fundamentalmente las personas que estén aquí sean estudiantes, ¿bien? Porque los que ya somos profesores, pues ya tenemos nuestro mundo más o menos hecho, ¿no? Pero ustedes tienen un mundo por venir y la mejor manera de ampliar ese mundo es ver el trabajo que hacen otras personas. Entonces, sin más, Chris, it's a nice pleasure to have you here. Professor Stevens, it's a nice pleasure to have you here. You are an outstanding chemist, and I'm happy for that, for having you here. And you are a very close friend of mine, and I am happy to have you here. So the floor is yours.
Thank you, Professor Martin Iglesias Artiago. Thank you, Martin. As you said, we know each other many, many years. And I hope he didn't tell too many bad stories in Spanish about me, but for sure I can tell also some bad stories about Martin later on, maybe after the lecture. It's an honor to be here. It's first time to come to Mexico City, and I'm overwhelmed to see the faculty, the university, 370,000 students. That's amazing. I mean, Ghent University in Belgium, we have about 45,000 students. So it's a factor almost 10. So I'm really amazed. So today I will talk about flow chemistry, and I have divided my talk in, let's say, two parts. The first part is rather general, to talk about advantages, disadvantages, some traps, some problems that you can see when you're using flow chemistry. And then in the second part, I will talk about the work we have been doing in flow chemistry with some examples, and also there are some benefits, mostly benefits, but also some problems. So when we talk about continuous flow chemistry, the alternative is batch chemistry, as you know, and we have been doing that since ancient times. So the Greeks, the Egyptians, when they had to prepare wine, beer in bigger amounts, the way they did it is you start from a small scale and then you go to a bigger vessel and then still a bigger vessel and so on and so on. And that's how petrochemistry has been doing since the last 150 years. So you start in the lab with a flask of, let's say, 5 ml, then you go to 100 ml, to 1 liter, and then you scale up to a reactor of a few cubic meters. So similar to the electronics industry, where you go to look at smaller and smaller dimensions, about 30 years ago, people started thinking in the same way in chemistry. What if we would do reactions in a continuous flow, but instead of using big pipes, as in petrochemistry, scale it down to millimeters, to micrometers, and let's see what's happened. Can we produce chemicals in a safe way, in a sustainable way? Maybe you have seen I'm working in engineering department, Faculty of Bioscience Engineering, so we're looking also a little bit to the engineering, and I'm working in the Department of Green Chemistry and Technology. So for us, sustainability is certainly one of the important things when we think about performing some reactions. So the idea is, let's do the chemistry in smaller scale, pumping reagents through small channels and then see what's going on. So we're moving from the initial start of chemistry to the classical batch type chemistry, and nowadays we're moving to racks of microreactors which are placed in parallel to produce bigger amounts of chemicals. So classically, we go from the lab setup to big distillation vessels or big reactor tanks, whereas the principle of continuous flow chemistry is to number up. So you will have a small reactor, which is mostly the size of a chip, and we will put this in parallel, so you will number up, have a lot of different small reactors, and the big advantage is, of course, that your reaction control is the same in every small reactor. While your volume goes up, the reaction control is the same, which is, of course, certainly not the case if you do the scale up in a reactor tank, because mass transfer will be different, temperature, heating will be different, and so on. So every time you need to optimize the scale up, while here you simply number up and the reaction will proceed as it proceeds in one small reactor. So what is really a very big advantage, and a few years ago we wrote a review together with Steve Lay, who is one of the big guys in continuous flow chemistry from Cambridge in the UK. And one of the things for continuous flow chemistry is that you can also tame hazardous chemistry. Chemistry which would not be possible to do in an industrial scale, because if you scale up the reaction, it would become too dangerous. Runaway reactions or reagents that are too toxic, and so on and so on. So that poses a big problem. And now all this, what is called forbidden chemistry, becomes possible if you're using continuous flow chemistry. And we're looking reactions of diazomethane, azide chemistry, cyanides, phosgene, nitration, and so on, becomes now possible to perform in a safe way on a big scale. So let me just go over the well-known advantages. I don't go in detail. I think most of the people know when we talk about continuous flow chemistry, what are the obvious advantages. You have a very good surface to volume. That's why you can control very well the temperature of the reaction. You have very good heat transfer capacity, so you can very efficiently heat or cool the reaction. There is continuous production, of course, but also very important, especially for the pharmaceutical industry, is the constant quality. Because you can control the conditions of the reaction so well in the chip that the quality of the product will be much more constant than if you produce it in a big tank reactor. And there will, of course, be a variability between different batches, whereas in flow, that change is minimized. And of course, it's well contained, so you only deal with very small amounts of reagents, so that's why the safety is also much higher, and you have a very good safety control. So let's look at one characteristic, for example, the surface to volume ratio. So if we talk about a flask in the lab of 100 ml, then you see that the surface to volume is about 1. So you have 1 cubic centimeter per, 1 square centimeter per cubic centimeter. If you look at a 1 cubic meter reactor, this surface to volume becomes 0.06. When you look at a microchannel of 100 micron, this is 200. So that means you have 200 times compared to a flask higher surface to volume. So that means that you can very efficiently cool and heat the reactor very fast, and that, of course, has a very important issue in industrial chemistry. So this is a calculation. It's not done by us, but this is a CFD calculation. When you mix a base and an acid, for example, sodium hydroxide and sulfuric acid, we all know this is a very exothermic reaction. And if you model it in a reactor, you see the red surface is the temperature, the high temperature, the volume of a high temperature in the reactor. So you see that a considerable volume of the reactor is overheated. Whereas if you do the same reactor in a 70 micron microchannel, you see that even after a few centimeters, all the heat has been dissipated from the channel. So that also illustrates the advantage and the capacity of continuous flow chemistry. So what is now so attractive for industry? Well, I have already said, scale-up becomes much more easy. The most important aspect is the fact that you can control dangerous reaction, but you have also a flexibility of synthetic capacity. As I showed that you number up the reactors, if your production goes down because the market is shrinking and you have to produce less compound, you can take, let's say, 50 of these reactors and use it for another production. Whereas if you have one big tank in your company, even if you fill it half, the volume is completely occupied. So you have also, from capacity point of view, a very strong case to switch to continuous flow chemistry. But maybe the most important thing is certainly for pharmaceutical companies, the fact that you can shorten the time to market. And that's, of course, very important in view of patents. So you're probably all familiar with this graph, which says something about developing pharmaceuticals in the industry. So if you want to have one FDA-approved drug on the market, it means that you will have to start more or less with 10,000 compounds in the lab to the screening to finally get one FDA-approved drug. So that's a quite good ratio in industry. Companies that get 1 out of 10,000, they are doing well. What does it mean? That especially here in the preclinical phase, so you screen your compounds, a lot of compounds drop out, but maybe in an enzymatic screen, you have about 250 compounds that give a positive signal. And from these 250, you need probably a few grams, a few hundred grams to do the toxicity testing and all kinds of different tests. Although you know that in the following phase, only 5 will survive. That means that for 245 compounds, you need to do the scale-up with all the problems associated with that. If you have a continuous flow process, you don't spend any time. You switch it on, you go home, you come back on Monday morning, and there's your compound. You just pump for a longer time, and you can produce 10 grams, 100 grams, a kilogram. You just need to pump for a longer time under the same conditions. So that's really an important issue why pharmaceutical industry is really paying a lot of attention to continuous flow chemistry. And as you know, more or less, the development of a pharmaceutical drug more or less costs €1 billion at the moment. So if you can save even a few weeks in development time, this is a major gain in profit for the company. So that's an important point why industry, and especially pharmaceutical industry, is interested in continuous flow chemistry. Of course, it's not all sunshine. There are also some problems. There is no technology without problems, without disadvantages. Also here there are some. When you look at a chip for continuous flow chemistry, these are maybe channels of 100 micron. Of course, if you have media with solids, it's quite obvious that you can run into trouble, that the small channels will block, and of course the flow will not be possible through the reactor. When you have highly viscous media, the same thing happens. You will have a pressure buildup in your reactor, and finally your pump will not be able to pump the solution through the reactor. For the first one, people are developing solutions already. Yeah? There are already a number of tricks how to deal with solids and continuous flow chemistry. Another one which we can deal with, but with a lot of problems, is solvent changes. If you want to couple one reaction to the next one, and the first one is probably done in toluene, the second one is in DMF, and the third one is in THF. I mean, it's not easy to connect these reactions because you will end up with a problem with your solvent. So you need to be able to do a solvent switch in between, and this is still a big problem today. And of course, when you have equilibrium reactions, that can be a problem also. In batch, if something precipitates out, we know that the equilibrium is shifted, but this will not happen. Well, it will happen in a flow reactor, but you don't want the precipitation. So equilibrium reactions could be a problem as well. But maybe a last general aspect I want to focus on, and which is maybe less obvious, and this is what is called in the literature the third stream problem. What is the third stream problem? Well, when you pump a reagent through a reactor, like a coiled reactor, and you give a pulse of a reagent with certain concentration, and you pump it through the reaction profile or the concentration profile will change. Here you have like a stepwise profile, and here you see you are getting like a bell-shaped curve. The same if you have something like that, you know, because of diffusion in the reactor, you will have a changing profile. So when you have a setup, you mix reagent 1 with reagent 2, you have a perfect profile, you start pumping, concentration goes up, but once it goes through a tubular reactor, you will end up with a profile going like this. And of course, if you need now to add a third reagent, you can pump a third stream here. But of course, if you want to control the ratio between this one and this one, you're in trouble. Because in the beginning, you will pump too much of the third reagent, then it will be quite okay in the middle, and then at the end, you will pump also too much of the third stream, which will have a completely different stoichiometry, and that can ruin your reaction. So how to deal with this? Well, luckily enough, we have already infrared sensors which can be put in line into your reactor, and this in-line infrared will measure the concentration profile, and with a computer, this profile will be pumped for the third reagent. So this profile will be pumped by the measurement of the infrared so that your stoichiometry in the reactor stays, for example, 1-to-1. And in this way, this has been illustrated very nicely in a paper of Steve Lay and Ian Baxendale for this very sensitive reaction. It's an enantioselective reaction. You have an ester, and you reduce it with dibol. So you reduce the ester to the aldehyde. It goes through a reactor. I don't want to go into details, but you get the aldehyde, and then you do an addition of a boron ester to the aldehyde to get the corresponding alcohol in a very nice enantioselective way. If the ratio of this compound with what comes out of the aldehyde is not 1-to-1, you will lose immensely on the yield and the enantioselectivity. So that's something maybe you would not think about in first instance, but this third stream principle is very crucial if you try to connect different reactions in one kind of setup, which we call telescoping of reactions. That's for what is the general thing. Let me now come to some examples which we did over the years. We started doing continuous flow chemistry somewhere in 2004 with some, and I gave some examples, early old examples, but also some recent examples. This is one of the very early examples we did. We published in 2007, and when we started, we thought, what would be the most difficult thing to do if you think about safety? Well, if you can control reactions with hydrocyanic acid, the gas that has been used in the concentration camps, this is extremely toxic. So if we can do that, we can probably do a lot of other things. So we went to search for a reaction which really needs hydrocyanic acid. And that was a reaction that was published by a German group. You take a 4-mol benzoic acid, you react it with an amine in methanol with potassium cyanide in the presence of acetic acid. And of course, if you have the potassium cyanide in the presence of acetic acid, you will generate immediately HCN. And you need this for the reaction to proceed. I will illustrate it immediately with the mechanism. And you get this kind of isochrominanes, which were produced as a kind of a mimic for a nucleobase to build it into DNA. So we looked at it very carefully, and we compared the flow chemistry with batch chemistry. And you see that if you do it in a 25 ml flask, you get about 200 times less HCN, which goes out of the reaction when you do it with continuous flow chemistry. When you do it in a 250 ml, it's about 100 times less HCN that you use in your continuous flow chemistry. That's already nice. And of course, safety is important because the HCN is completely contained, and once it reacts, it doesn't come out of the reactor anymore. There was one additional problem, because this compound is a solid. And so when you produce it, at the end of the reactor, the compound starts crystallizing. And as the reaction goes further, the crystals are crystallizing into the reactor. And after a certain moment, of course, the flow stops. So what could we do? And this is one of the solutions. If you have this problem, I'm not sure if this little movie will work here. Let's see. No, it doesn't, but it's not important. I can comment on it. It's quite obvious what happens. What we do is we pump in a fluor inert solvent. So it's a fluor solvent which doesn't mix with the reaction mixture. So you get one droplet of fluor inert and one droplet of reaction medium. And even when you get crystals in these little droplets, they get pushed out by the very hydrophobic solvent, and so they don't get the chance to crystallize into the reactor. And when everything drops out, the two mixtures separate because they are immiscible, and you take the fluor inert solvent and use it again. So you simply recycle the fluorous solvent and you solve your problem. Oh, there it goes. Okay, well, not much to see about that. So that's what we did. This is such a reactor where we did the reaction. It's a Cpc reactor. It's one of the earlier models from Germany. At the moment, this company is already bankrupt. They were too early. It happens when you come with a new technology and you're very early. It can happen that you don't get enough clients, but it worked perfectly. You have the two pumps here, the reactor here, which is almost the size of a hand, and then you have the residence time unit just for the reaction mixture to give some time to react completely. So what happens, we mix the 4-methylbenzoic acid and the acetic acid together, and the amine together with potassium cyanide. So here, potassium cyanide in alkaline medium, no problem at all. But once they mix in the reactor, you form the hydrocyanic acid, and that reacts straight away, and you form the isochrominone, and we could do that in about 2 grams per hour. That means that you can produce very easily 50 grams per day. So for pharmaceutical companies, when you have a week, you can produce, with such a simple reactor, you can produce 300, 400 grams a week. So here's the mechanism. You have the aldehyde or the 4-methyl group reacts with the amine, forming the corresponding imine. And of course, the potassium cyanide together with the acetic acid forms the hydrocyanic acid. It protonates nitrogen, attack of cyanide to have the cyanoamine, which is now attacked by the carboxylic acid. And enamine tautomerism leads in one step. So what drips out of the reactor is the isochrominone. At that time, I thought it was a nice example to illustrate the power of continuous flow chemistry. Later on, we had a company in Belgium, Agfa, who was producing this kind of tribromo sulfone, because it's used as a preservative in all kinds of films. But the problem here, if you do this reaction, you have a sulfone and you treat this with potassium hypobromite, you get some tribromo compound, but you get a terrible mixture of the monobromo, the dibromo, and the tribromo. And this was a problem. So they wanted to challenge us and say, okay, you advocate continuous flow chemistry. Here's a nice example. Go ahead. So we wanted to see if we could produce in an easy way the tribromo compounds. And that's how it finally looked. So we start with bromine, which we mix with potassium hydroxide. And we had to do this in a continuous stirred reactor. It's just a kind of a tube. And then we pump it from here. If we really do this in flow, it didn't work properly. So we had to adjust a little bit the idea. We mix it first, and then we pump it from here into a Unixis. This is the Unixis reactor. It's also the size of one hand, together with the substrate, and it simply flows through it 3 minutes, 85 degrees, and we got more than 99% yield of the tribromo compound. No problems with dibromo, no problems with monobromo. It works fine, 12.1 gram in 5 hours. So they were very excited. They worked further on this in their company, and now the last news I heard from them is they were doing a bromination reaction, not this one, a bromination reaction with 500 kilograms of bromine in a garden hose. They just went to the store, they buy a garden hose, they pump the bromine through the garden hose, and they got the compound. It doesn't work always like that, but sometimes you're lucky. And if your garden hose gets too much corrosion, you throw it away and you buy a new one. So sometimes it works very nicely. And so you see here, we made a number of different compounds. Throughput in grams a day is reasonable because this is a setup in a hood. You know the ECA plates, so you know more or less this fills like one small hood, and you can produce 50 grams of these kind of nasty compounds a day. The yield from quantitative to about, well, this one was a problematic 48% yield. Then we went on. Bromine, a lot of brominated compounds are produced, not always as a final compound, but of course as an intermediate. Brominated compounds are very, very important. Think about Suzuki couplings, whatever type of modern couplings, you will need a lot of brominated compounds as an intermediate. So we went on to deal with bromination technology, and here we looked at oxidative bromination. So if bromine itself, it's quite nasty compounds, can we avoid to use bromine as a liquid reagent? Can we generate bromine and then use that in a safer way? So here we use hydrobromic acid or potassium bromide, and as an oxidant we use bleach. So the bleach will oxidize the bromide to the bromine. Then we pump the substrate together with this reagent flow through another reactor at 50 degrees. You brominate your products, and then you pump in a reagent to quench the bromine, and so you get all your brominated products without any bromine at the end of the reaction. It looks simple, but we spent about 3 years to optimize this type of reactions for a number of polybrominated compounds. You think about brominated phenols, you think about brominated bisphenols, hexenes, or even coloring reagents, eosin, and so on. It works, but we have to be honest, there is also a drawback. Sometimes you need to use a quite big excess in order to introduce all these bromine atoms. Here 6, here 4, here 3, and so on. So it's not always one-to-one. Reactivity can play a big role here. Here another example where we looked at telescoping reactions, because I think this is really the challenge for the industry, trying to connect when we think about a synthetic pathway, and we do it in batch. After every reaction, we do a workup, we evaporate the solvent, we purify, crystallize, distill, chromatograph it, but actually to have it very sustainable, we want to connect one reaction to the other, and only at the final stage do the purification. And one reagent that really got our attention is this one. This is a lithiated methoxyalene, and Professor Reissig from Berlin, I think he has about 50 or 60 papers on using this kind of lithiated alene to a very big variety of heterocyclic compounds. A number of different compounds. The problem is that he has to produce this on small scale. If you try to scale up this reagent, you run into trouble. You can make it on about 20 grams, which is, or 10 grams, but then problems start arising. So we thought, can we translate this into a continuous flow process? And so this is the This is the synthetic sequence that has been published by Professor Reissig. You start from proper gel alcohol, you methylate with dimethyl sulfate, not the most green or the most favorable reagent you want to use. Then with T-butoxide, you get to the alene, and then N-butyl lithium lithiates the alpha proton here to the lithiated methoxyalene, and then you can add an electrophile and get all kinds of different reagents. This is just a grip out of the many publications of Professor Reissig, also a very interesting review on the use of lithiated methoxyalene. And for example, here it reacts with a ketone, and you get all kinds of rearrangements, or you react it with cyclohexanone, it adds to the alcohol, and then it ring closes to a number of heterocyclic compounds. So that was the purpose. We wanted to produce this lithiated methoxyalene, and to cut a very long story short, we have not been able to put it in one flow. We have been able to put it in two kind of separate processes, but two flow processes. And the reason was that the first step, we had to do it in water. We have not been able to find a good solvent that was compatible. Remind, the last step is a lithiation. Of course, the lithiation with butyl lithium is not compatible with water, so we had to split the two reactions. So here, dimethyl sulfate with proper gel alcohol, 55 degrees, 30 minutes, and you get 95% yield. We can do the extraction in flow. There are many ways you can do also extractions in flow, and so we could come up with a nice continuous synthesis of this methylated proper gel alcohol. And then we telescoped all the rest in THF. So you start with the methoxyalkyne, you dissolve it in THF. You need some sonification to get everything well in solution, 55 degrees. And then we add the T-butoxide. So here the T-butoxide and THF need some time to do a job to dissolve. So we need some sonication in the reactor bath. We generate with 98% yield the alene, and then we add butyl lithium and hexane, 1.05 equivalent, so very efficient. We put it through a static mixture, and then we get a lithiated compound. And just to show that it works, we added also a ketone benzophenone to make this kind of alcohol as an example. And so we have been able to produce about 30 grams per hour of this lithiated methoxyalene in flow in 31 minutes. So now you don't have to make every time a batch again of 10 to 15 grams. You can continuously produce about 30 grams per hour of this lithiated methoxyalene. Maybe a bit more quickly, also one technology that is really fitted with continuous flow chemistry is photochemistry. Photochemistry suffers because the penetration depth of your light in a solvent is very limited. It's only 0.5 centimeter, and then the intensity of the light is not high enough to do something with the reagent. So if you have a flow reactor with a channel width of about 2 millimeters, you can completely irradiate the channel, and in this way you can very effectively do photochemistry. Because the fact that we don't see a lot of photochemistry in industry is simply because it's not efficient. If you have a big tank reactor with the light, you need to stir forever before every reagent has passed in a space of 0.5 centimeter in front of this lamp. So in this way, we can now really take advantage of a number of characteristics of continuous flow chemistry to do photochemistry short diffusion lengths, short time of illumination, so you prevent degradation of your end product, good control of your illumination strength and temperature, and you can play with wavelength and so on and so on. So we have been working together with Oliver Kappe from Graz, who is one of the top labs in continuous flow chemistry, on this type of molecules at HMF. It's hydroxymethyl furfural, which you can produce easily from different types of sugars, glucose, fructose. So it's a bio-based molecule who has a lot of potential. You can transform it in dimethylfuran, which is a biofuel. You can transform it to the dicarboxylic acid, which is used in polymer chemistry, PET-type analogs, and you can have it also as a diol in polymer chemistry. The big problem is that this compound is very, very labile and gives a lot of side reactions, so difficult to work with. So this was, again, something which was published by some French chemists a long time ago, but you get a mixture of compounds. So when you have the HMF, you generate the singlet oxygen with your light, and then you get the 4+2 cycloaddition, and the methanol, which is a solvent in the reaction, adds to the aldehyde, ring opens the Diels-Alder product, and you get to this compound, this butenolide that you really want, and you get some side products if you do that in batch. So we have been working on that together with Oliver Kappe to do that in flow. And here you have your oxygen flow, a mass flow controller, your hydroxymethyl furfural methanol. You pump it through your reactor in about an hour, and you get to also a mixture of compounds, but the ratio is much, much better. Here, I don't want to go in view of the time to all the details, but it was very important to increase the pressure of the oxygen. So we really had to work with a back pressure regulator, which really allows you to build up the pressure in the reactor. And so when we used about 70 bar of oxygen in the reactor, we got quite good yields with a nice ratio of products that we could isolate. And so we have been able to produce a whole set of different type of products, which some of which were not described before. We have to be honest, some of them we were not able to isolate. They degraded immediately. So that has been quite a challenge, and that we published in 2015 in the Chemsys Chem. Two final examples quickly. When we talk about esters, in every first year course, when you need to make an ester, what do? You take an acid chloride, you take an alcohol, and you add the base. You add the base because the HCl that is formed in the reaction should be trapped by the amine, mostly triethylamine or another amine, in order to push the reaction to completion. And I was very surprised, and it's because of a mistake of a student. They forgot to add the base. And what happened? It worked as well. So in flow, you don't have to add the base. You simply take the acid chloride, you take the alcohol, you pump them together in ether, and what comes out, or in the alcohol itself, and what comes out is the ester, completely the ester. You can say, well, what's the big deal here? Well, for industry, this is a big deal. First of all, you don't need the amine to add, which is already a saving. But secondly, you don't need to do an aqueous workup to remove the triethylamine hydrochloride. And so you don't need to dry your product after all. So the setup is this. You take the acid chloride, you pump the alcohol, you get the ester, and then we flow some nitrogen gas through the ester to remove the hydrochloride which is formed as a gas, and that you take up in water, so you get here an aqueous solution of HCl and your pure ester. You simply evaporate your solvent or the excess of alcohol, methanol, ethanol, isopropanol, whatever ester you want to produce, and you get very high yields of the ester. And this is one of the simplest reactions, but we have been able to publish this in Green Chemistry, the most basic organic chemistry reaction we teach to first-year organic chemistry students. The last example, and this is the most amazing example we have done in our lab. I couldn't believe what we saw, and this is when we were asked to produce a Sol-Ketal T-butyl ether. So you know when you produce biodiesel, you take a vegetable oil and you transform it into the metal ester, and you get on the one side glycerol and on the other side biodiesel. So we were asked to use this glycerol, which is a terrible brown syrup with a lot of alkaline, a lot of sodium hydroxide inside, use this to produce this compound, Sol-Ketal T-butyl ether. And this is used in industry to mix with biodiesel to improve the burning characteristics of the biodiesel. It reduces the small particles that are formed. It gives an improved combustion in the engine, and also the ignition is a lot better of your biodiesel. So that was a process that is done in batch. It's done on a 10,000 ton scale per year for the company we were working for, and they asked us, can you do this in flow? 10,000 tons per year, because that is also one thing that people think, if you talk about flow, you talk about micrograms or milligrams or grams of compound. You can also talk about 10,000 tons of compound. So what is the process? You take glycerol, you mix it with acetone. With sulfuric acid, you form the ketal, the Sol-Ketal, and this is then reacted with isobutene in acidic medium. So you know isobutene and acid, this is ideal to do polymerization, cationic polymerization, so you can expect a lot of trouble. And you form the Sol-Ketal T-butyl ether. So what we did in flow, we did first some calculations, and we found out that you need about 4 equivalents of acetone to produce the Sol-Ketal in the presence of sulfuric acid. Yeah? I don't want to go through all the details because this is published, but what we saw is that we need to do a pre-drying of the glycerol. If we really take the glycerol from the biodiesel production and we use it like this, the yields are not very high. We had to pre-dry a little bit, and so if we remove some water less than 1%, you see that we get about 70% of Sol-Ketal, which is not great. But then what really made the change is that, and this is a bit counterintuitive, when we increased the speed of pumping the reagents through the reactor, we pumped 3 times faster. That means that the residence time is 3 times shorter, and normally you would expect that your yield would drop. Here it's just the opposite. If you pump 3 times faster, the yield jumps from 70% to 98% yield. And in the beginning, we didn't understand what was going on, but now we know, because glycerol and acetone, they don't mix very well. But the Sol-Ketal, once you form a little bit of Sol-Ketal, this helps to dissolve the acetone and to dissolve the glycerol. So it's a kind of autocatalytic process. Once you get a little bit of this, the rest dissolves much better. And so when we pump faster, they get they mix better, you get a little bit of this, and then the reaction takes off. So that's why, which is counterintuitive, if you pump faster, that you get a much better reaction. And then the second step, reaction with isobutene, there we saw that we should use it as a liquid, and so we could produce this compound STBE. I will speed up a little bit. Just here what is a lot of figures, but this is the most important. In industry, the first reaction in batch takes 12 hours, the second takes 9 hours, and in flow with excess of acetone and 2 equivalents of isobutene, in flow we get 26 seconds for step 1, 41 seconds for step 2. So instead of 21 hours, we got 1 minute and 7 seconds to do this reaction, which is amazing. That's the most extreme example we ever saw to speed up reactions in flow, and that is because of this autocatalytic kind of reaction. So that was completely with an engineering bureau. This was optimized to indeed produce 12,000 tons a year with acetone, glycerin, sulfuric acid, and isobutene. This was Corning and BioValue optimized this theoretical study. Unfortunately, Corning was sold to another company and they never built it. The technology was working, it was all was calculated, but they never built it. And that's why we can talk about it today. So in every disadvantage, there is an advantage. So that's it, a few slides. We in the lab, we tried to buy industrial systems, because if you want to work for industry, they want to use the equipment. And so if you build something on your own, it's not very valuable for industry. So that's why we normally use equipment that is on the market. And as you see, the predictions of flow chemistry are amazing. They think about $3 billion in 2026. And that's the way forward. And there are a few nice examples of the team of Klaus Jensen and Tim Jameson in MIT, where they produce a number of APIs, pharmaceutical compounds, drugs, in a kind of refrigerator type setup on a squid, where they introduce everything in a box which is as big as this lectern here, which is amazing to produce these kind of APIs. So that's probably a view of the future, how a pharmaceutical company will look in a few years with a lot of microreactors, a lot of pumps, and trying to control the flow. I want to thank the people of my group. This is our Synbiog group. We are 4 professors at our faculty, and we have a group of about 40 to 50 people with master students, PhDs, and postdocs. So thanks to them, I could talk about our work here. And the last thing I want to do is to convince you to come to visit us in Ghent. And these are a few pictures of Ghent. It's a medieval city, which is quite nice to walk around and to have a beer. And if this is not good enough, we still have some other things to convince you. Our Belgian beers, our Belgian fries, and the chocolates. But above all, we hope you can come to discuss about good science. Thank you very much for your attention.
Well, thank you, Professor Steven, for this interesting talk. We're now open for questions. Tenemos tiempo ahora para preguntas. Braulio.
Thank you very much. It was a wonderful presentation. So I was wondering if in the case that you have the flow already working, when you work with crystalline compounds, it wouldn't be possible to reduce also the size of the crystals to work with nanocrystalline suspensions and get, that will allow you to get some control of the specificity of the reaction, and also as you reduce the size, you may introduce a better yields in the photochemistry that you showed us.
There are some very nice papers, one of Steve Buchwald, and he was one of the first ones to put under the reactor like a piezoelectric foil, and then you put a current and this starts vibrating, and so the vibration will reduce the size of the particles that are formed in the reactor. And so I think he used like 50 hertz of vibration, and then the particle size was lower than 100 micron. And what you most of the time in flow processes, if the particle size is smaller than 100 micron, there's no problem. It keeps going. But once these particles stick together, they start agglomerating in, then you are in trouble. And another, as you said, the formation of nanocrystals, when you flow a solvent and a non-solvent together, there are some examples where you form nanocrystals, and also there, when the particle size is less than 100 micron, you're in good shape most of the time.
¿Más preguntas? Okay, I have one. Well, one of your last slides, you show a view of the future. Well, how far is the future? How far is this future? How far are we from generalization? You know that in the early 80s, everybody was working with microwave chemistry, and it became popular. Now, because they were using a house microwave. Now, the microwave for chemistry are expensive, but they are not out of the reach of. We have one, but how expensive and how far is this from generalization?
Very good question. I think you have to divide the industry. When you look at the chemical industry and you look at the big productions of chemicals, like the big volumes, I don't think their microreactor technology will take over. That will stay big batch reactors. You don't have to switch to continuous flow just to switch. You only have to switch if there is an advantage. If you really can make it more sustainable, less expensive. So for the bulk chemicals, the common chemicals, I don't think it will take over. However, in the pharmaceutical industry, I think we are there already. Janssen Pharmaceutica in Beerse is now building the first completely line for continuous flow chemistry, up to tableting and putting in the box everything in one go. And it's now being validated by the FDA, and they hope it will be it will be completely ready and to be sold on the market in 2 years. So in the pharmaceutical industry, because of the constant quality and the control, I think there it really will take over in a few years. Also, FDA has been pushing the technology the last 5 years. There are a number of publications of the FDA where they really want to convince the pharmaceutical industry to look more carefully to continuous flow chemistry. A second reason why in the normal industry, why they don't switch immediately is that a number of big companies, BASF, Bayer, and the big ones, they have their reactors and they're paid off. They're for free. So why would you do a major investment in continuous flow chemistry if your reactors that you have are for free? So, you know, there's not only the technological problems, there are also the financial and the economical things. So for the batch industry, the big volumes, I think they will stick to batch, but the fine chemicals, the pharmaceuticals, I think this is coming soon.
Thank you very much. Bueno, mañana nosotros vamos a tener una plática adicional. I'm speaking in Spanish. We say terrible things about this. Vamos a tener una plática que va a estar relacionada con la química del fósforo, o sea, algo completamente distinto. Algo completamente distinto a lo que vimos hoy. Entonces están todos invitados. Professor Stevens, thank you for being here. Thank you for accepting this invitation, and thank you for this talk that opens. Well, I am speaking for me. This opens a new word. I will use the word of Aldous Huxley, but in the good sentence, brave new world. It is something that is the future. So thank you for this talk. Por favor, agradezcámosle al profesor la conferencia y su presencia aquí. Están todos invitados a mañana.
Thank you very much.